Hello, this is Professor Arai in section 5.1 hypothesis tests using normal distributions. So in chapter 3 and chapter 4, we heavily investigated randomization and bootstrap distributions. And if you recall, they all looked like this. We noticed that they all look like a bell-shaped curve. We actually can draw a smooth line on top of these curves. And for this section, we will call this new line or this smooth line of a bell-shaped curve a normal distribution. So a normal distribution is the symmetric bell-shaped curve that we have seen in most of those distributions, bootstrap and randomization. And we can actually donate to the normal distribution by the letter n. And we can write the name of the curve by saying n, parenthesis, the mean of the curve, and the standard deviation. So we can write a name to each curve describing the whole thing. So once you read the name of the curve, you can actually imagine how the curve is going to look like. So if you look at here, the name N01, so you know this curve is going to be a normal distribution. That means it's going to be smooth, symmetric, bell-shaped curve. You know that the mean of this curve is going to be at 0, and you know that the standard deviation will be 1. Same thing for this curve here over here. You know this is going to be a bell shape, has a mean of 2, and standard deviation of 1. Notice how each time, whenever the standard deviation gets higher, the normal curve gets wider. And this is not new. We've talked about this before. The larger the standard deviation, the more uncertainty you will have. So let's look at the first example. The question is, which normal distribution should we use to approximate this? So again, you are given the graph, and in this section, we are hoping to name the graph by a single line using these terms. So I look over here, this is a bell-shaped curve, so I can use the letter n to it. So this is a normal distribution. This normal distribution is centered at 0, so the mean is 0. So I know A and B are options for me to consider. However, C and D are not. Now the question is, what is the standard deviation? Ignoring the fact that I can see the standard deviation here, I can calculate the standard deviation by finding the distance between the center and the end of the bell dividing by 2. So from 0 to 0.10 divided by 2 is about 0.05. So the normal distribution in this case would be this: n parentheses 0, which donate to the center, comma 0.056, which represent the standard deviation. Now, for this section, we will use a new feature from StatKey. So let's look at this new concept, which is the area under the curve. In example 1, you are asked to find the area to the right of 95 in a normal distribution with mean 80 and standard deviation 10. So you have the answer, but let's see how we can find it using StatKey. So keep in mind we have the mean 80 and standard deviation 10. So when you go to StatKey, you will go to the word normal this time for this section. And once you are in there, you will edit the parameters to enter what you are given. You are given the mean to be 80 and the standard deviation to be 10. So once you do that, you create this normal distribution that is centered at 80 and has a standard deviation of 10. And the question is, find the area to the right of 95. So you will click right, and you will adjust the cutoff to 95. And by doing so, you will get the area under the curve. And here, the area is 0.067. And this is given to you in your PowerPoint. This example is similar to question 15 in the homework that you'll have for 5.1. The second concept of the section is the standard normal distribution. Notice how we added the word standard, and this will change a lot of the concept that we just covered. So the standard normal distribution is also a normal distribution, but is written as N01. Meaning all standard normal distribution have the mean as 0 and the standard deviation of 1. The other thing that you need to know is that whenever we are in the standard normal distribution, we need to convert the values from the normal distribution to the standard normal distribution, and we will use the z-score to do so. If you remember, z-score from chapter 2 was z equals the statistic minus the mean over the standard deviation. In other words, you can be given the normal distribution, as we've seen with the mean and the standard deviation. You will convert the values using the z-score formula, and once you convert them, then you can apply them to this new standard normal distribution. Now we use the standard normal distribution because all normal distributions look the same except with the horizontal scale. So to make them more common, we use this standard normal distribution. So let me show you some examples. What do I mean by that? So for example 2, it says find the specified area for a standard normal distribution and sketch the area using StatKey. So we need to look at the area to the left of z equals negative 0.8. Now, since I'm finding the area in the standard normal distribution, so I'm keeping in mind that the mean will be 0 and the standard deviation will be 1. So I'm going back to StatKey. Same place, I'll go to normal. This time, since I need it to be in the standard normal distribution, I'll keep the mean as 0 and the standard deviation is 1. And the values that I need to cut off my scale with needs to be in the z values. So I look here, I have the values given to me in the z values. So I have z equals negative 0.8, and they need me to find the area to the left of that. So you'll do the same thing. To the left, the cutoff is negative 0.8. And the area will be 0.212. Same thing. Okay, let's find the area to the right of z equals 1.2. So this time again, I have the standard normal distribution, mean 0, standard deviation is 1, to the right of z equal 1.2. So right of 1.2. And the area is this number here, 0.115 or 0.115. And this is it so it's the same method. The only difference is that the mean will be 0 and the standard deviation will be 1. Okay, let's look at example 3. Example 3 will tie example 1 and example 2 together. So in example 1, we found the area to the right of 95 in a normal distribution with mean 80 and standard deviation 10. This time, they need us to find the z-score first for 95 and then use the standard normal distribution to find the area. So remember, again, you cannot use the standard normal distribution unless you convert everything using the z-score formula. So the z-score for 95 is the statistic minus the mean over the standard deviation. So I'm using the formula over here. The statistic, which is 95, minus the mean, which was 80, over standard deviation, which is 10. So if I do that, the z-score for 95 will be 1.5. So now I have the conversion in z's, and I need to find the area under the curve to the right of this z-score. So I'll go to StatKey. I will keep it in the standard normal distribution, and this is to the right of the z-score was 1.5. And the area is exactly the same. In example 3, the area is 0.67, is exactly the same as the area in example 1. So the difference is that in example 1 we are using the normal distribution, using the mean and the standard deviation and the raw data. And in example 3 we are using the standard normal distribution. This time the mean is 0, the standard deviation is 1, and instead of using the raw data we will use the z-score for these data. Okay. Next concept is the central limit theorem. The fact that so many sampling, bootstrap, and randomization distribution follow a normal distribution is not a coincidence. Statistical theory confirms that for a large enough sample size, the distribution of many common sample statistics such as mean, proportion, difference in means, difference in proportions will follow the pattern of a normal distribution. These results follow from one of the most important results of statistics, and that is called the central limit theorem. So the central limit theorem says for random samples with a sufficiently large sample size, the distribution of many common sample statistics can be approximated with a normal distribution. Basically, we're saying the larger the sample sizes, the more normal the distribution of the statistic will be. Now, the word sufficiently large will be discussed in details more in chapter 6. Okay, here's a question. If a randomization distribution is normally distributed, we can write it as, so let's remember, randomization distribution is always centered around the null, exactly. So the mean will be the null value and the standard deviation will be the standard error. So I can write the randomization distribution as n parenthesis null value comma SE. So I need you to write this one down. This is a very important part of this section, which is the relationship between the p-value and the normal distribution. The normal distribution that is best approximates a bell-shaped randomization distribution has a mean equal to the null value of the parameter. So when we are looking at the randomization, we can write it as n because most of the time it's going to be a normal distribution. It is centered around the null and has a standard deviation that is equal to the standard error. Now we can use this to find the p-value. When the randomization distribution is shaped like a normal distribution, p-value can be found as the proportion of this normal distribution beyond the observed sample statistic in the direction of the alternative, or twice the smaller tail of the two-tail test. What does that mean? It means, you know how we did finding the area under the curve in example 1 and 2? In those examples, we were actually finding the p-values. And this is the connection. If we can write the normal distribution as if we can draw the randomization distribution as a normal distribution, we can actually find the area under the curve beyond the observed value, and that area will be the p-value. So let's look at example 4. Many people pay more to eat organic food, but does eating organic food actually offer health benefits? In an experiment, scientists randomly divided fruit flies into 2 groups and fed one group conventional food and the other group the same type of food but the organic version. They then followed the flies and measured the flies' longevity, basically how long did they live. After 13 days, 318 of the 500 flies fed organic potatoes were still alive, as compared to 285 out of the 500 flies fed conventional food or conventional potatoes. Part A is asking state the null and alternative hypothesis for the test to investigate whether eating organic potatoes improve survival of fruit flies. So let's look at the information here. We have 2 groups and we have 2 proportions. So in this case, to write the null and the alternative, we will write them using what we learned about the difference in proportion. In this case, the null will be the proportion of the flies who ate the organic food and survived longer is equal to the proportion of the fruit flies who ate the conventional food. In the alternative, we're saying that the proportion of the flies that will live longer after eating organic food will be larger than the proportion of the fruit flies who ate the conventional food. Part B is asking, find the p-value using randomization distribution. Basically, find the p-value the way you learned it in chapter 4. So let's do this. So let's remember those numbers. We will need them. So let's go to StatKey. Find the p-value. So the way we found the p-value in chapter 4 is we went to the randomization hypothesis test. This is difference in proportion. And we edited our data to match what we have. For now, we have P1, the flies that ate organic potatoes, were 318 out of 500. So you will enter this in here, 318 out of 500. The other group, or group 2, the flies that ate conventional potatoes, were 285 out of 500. So when you enter this information, you will find the difference in group 1 minus group 2, or p hat 1 minus p hat 2 is equal to 0.066. So the way we did this, we generated several thousands of samples. And then this was a right tail test. We adjusted the cutoff 0.066. In doing so, we got the p-value to be 0.02. Now keep in mind, if you're doing this at home, you might have a slightly different p-value, but it should be similar. Not the same, but similar. So the p-value was 0.02. This is using the randomization method from chapter 4. Now, when I did this earlier, my p-value was 0.024. Again, every time you change it, it might be a little bit different. But what I needed to focus on is that when we got this p-value, we can actually find the standard error in here. And we will need this in a minute, because in part C, they asked us, what is the normal distribution approximated, that approximate the randomization distribution? So remember, the normal distribution is named based on the mean and the standard error. So in this case, we can write this as normal distribution 0, 0.032, whatever standard error you have. And this would be the normal distribution. Now part D is asking us to find the p-value using the new method, using the normal distribution. So let's go to StatKey one more time. And this time we'll go to the normal distribution. And we will edit the parameter because this is normal. So the mean was at 0. And the standard error or standard deviation was at 0.032. And we are looking to the right of the statistic, and our statistic was 0.066. So this is the difference in proportion. And if we do this, we will find the p-value using the normal distribution. Notice how the p-value is exactly the same as the previous one. So p-value is 0.02. So whether we use the randomization method that we learned in chapter 4 or the normal distribution method, we should get a similar p-value. Now let me show you a third method. A third method is using the standard normal distribution. Now let's see, what do we remember? Standard normal distribution meaning the mean will be 0 and the standard deviation will be 1. And as I said, we cannot enter any values until we convert them into the z-score. So in this case, before we find the p-value, we need to convert the 0.066, this is our statistic, into the z-score of that. So the z-score formula is the statistic minus the mean. The mean here is the null, 0, divided by the standard error, which is 0.032. Once you find the z-score, now you can actually find the p-value. So again, remember, you cannot find the p-value unless you convert your raw data. This is my raw data into the z-score using this formula. So let's look at this. Let's go to StatKey one more time. And for standard normal, you will go into normal. You will keep these parameters the same. You still need the mean to be 0 and the standard deviation to be 1. And this is the right tail test, but it is to the right of the z-score that you just found. And the z-score is 2.06. So I'm going to adjust my cutoff to 2.06. And once you adjust the cutoff, the p-value will be this number over here. And as you can see, all three p-values are very similar to each other, if not the same. So these are the three methods to find the p-value. You can either find the p-value using the randomization distribution, or you can find the p-value using the normal distribution, keeping the null and the standard deviation. Or the third method, you can use it using the standard normal distribution. So here it should supposed to say standard normal distribution because it's centered at the 0 and has a standard deviation of 1. And again, these are slightly different numbers because each time you enter your numbers in your StatKey, you will get slightly different numbers. But what you can see is in each case, the p-values are very similar to each other. Okay, let's try the last example, example 5. So this is again similar to example 4. So if you didn't get example 4, this will be helpful. Try to do this example before you listen to me so you can see if you got it or not. So for example 5, it says, suppose we want to test the hypothesis. You have the null p equals 0.5 versus the alternative p larger than 0.5 using sample proportion of 520 out of 1000. Part A is asking you to use the randomization method to find the p-value. So let's do this together. So remember these numbers, 520 out of 1000. So to find the p-value using the randomization method, this is a single proportion problem. You will edit your data, and this is 520 out of 1000. Once you have your data, you will generate several thousands of samples. And then you will follow the alternative. The alternative is larger than, so you know this is a right tail test. And you adjust the cutoff to your sample statistic. My sample statistic is 0.52, so you'll enter that here. Okay, so if you enter the 0.52, your p-value should be similar to this number. So keep this number in mind. The p-value is 0.098, or it could be 0. If I round up, it'll be 0.1. So anything that is closer to this number will be a good representation for the p-value. Part B is asking, what is the standard error from the randomization distribution? So for this one, you will go back to your randomization distribution, and the standard error should be always in this corner. So the standard error is 0.015. 0.015. Part C, model the randomization distribution with normal distribution with the mean of 0.5. I'm given the mean. Remember, you always follow the null from the null hypothesis, and the standard deviation using the standard error that you found. So we're finding the p-value using the normal distribution. Normal distribution. So let's go over here. So normal distribution. I'm going to edit the parameter. The mean in this case is the null. So 0.5, And the standard deviation is the standard error that I just found, which is 0.015. And for the normal distribution, you don't have to convert. You should be fine. You only convert for the standard normal distribution. So the cutoff was at 0.52. So this is a right tail. And you will adjust your cutoff to the same one, 0.52. So if you're wondering where is this coming from, this is your p-hat, your sample statistic that you entered. So the p-hat, I'm getting the p-hat from here. 520 divided by 1000. So if I do that, I get a p-value that is equal to 0.091. It's very similar to the previous one. The previous one was 0.098. So both of them, they will round up to 0.1. So this is good. Now for part D is asking, find the standardized test statistic. So this is the fancy name for the Z. So the way we found this, Z equal the sample statistic, which is 0.52, minus the mean, which is 0.5, divided by the standard error, which is 0.016. So I did this previously. This time our standard error is 0.015, but it should be okay. So if we round up, it should be similar to this number. So the Z-score for this sample statistic, which is 0.52, is 1.25. After finding the Z, find the P using the standardized or the standard normal distribution. So let's do this. Remember, for the standard normal distribution, we keep the mean 0 and the standard deviation 1. So we keep them here, and we only enter the Z-scores. So this is a right tail, and the Z-score is, let me get the Z-score again, it's 1.25. So this is my cutoff, 1.25. And if I plug in this Z-score, I should get a very similar p-value, which I did. The p-value is about 0.1. So all three methods, whether you are using your randomization to find the p-value, or the normal distribution, or the standard normal distribution, they all should give you the same p-values. The differences are in the randomization distribution, you're entering the null. You're generating several samples to get the SE, and then you are adjusting the cutoff to get the p-value. For the normal distribution, you're using the null mean, and you're using the standard error from the previous randomization, and then you are using your sample statistic as the cutoff to get the p-value. And lastly, for the standard normal distribution, the mean is 0 and the deviation, the standard deviation is 1. The only thing that you need to do is you need to convert your raw data to a Z-score using the formula. And once you do that, you will do the same thing. You will adjust your cutoff and you should get the p-value. All three p-values should be similar. They're not going to be the same, but they should be similar. Now, one last deeper look before we end this section. I need you to keep this in mind. We will go over it again in 5.2. But in general, whenever you are finding the Z-score, remember when we talked about the 95 rule? The 95 rule is always between the -2 and 2 for Z-score. So we know if we are getting something larger than that, then we will get extreme values. So if your Z-score is 1.29 or 1.25, like example 5, we know that the p-value will be relatively large. However, if our Z-score is extreme toward the extreme, meaning larger than 2 and less than -2, then we will have a more extreme value, meaning our p-value will be relatively small. So in summary for this section, you need to remember what is the normal distribution, how to write it down using the mean and the standard deviation. You need to know what is the standard normal distribution and how to write it down. You need to know the standardized test statistic, the Z. This is its formula. And finally, this is the main goal of this section, is if your distribution of the statistic is normal, we can actually find the z and use the standard normal distribution to find the p-value. And that's it for 5.1. Thank you.